just want to make sure we're...
Yeah.
You're live.
Okay. All right. Cool.
Awesome. Hello, everyone. We are Project Zephyr. We are Supersonic recovery systems coming from Embry-Riddle in Daytona Beach, Florida, and we're going to present our project to you, what we've done, what it's about, and kind of overview that whole thing. We are going to be monitoring your questions throughout the presentation, but we'll come back at the end to answer them and go through all of them if that is okay. And we're going to get started here. So you want to present? Cheers.
Yeah.
So hi, I'm Rebecca Zurich. I am a junior in aerospace engineering and here at Embry-Riddle. And I am the program lead of Project Zephyr, so I organize and lead this whole project.
Hi, I'm Nathan O'Hara. I'm a sophomore in aerospace engineering, and I am the avionics lead for Zephyr.
I'm Graham Holtz. I'm a sophomore in aerospace engineering, and I am the lead for the numerical simulations.
My name's Eric. I'm the aerodynamics sub-team lead, and I'm a senior studying aerospace engineering.
I'm Spencer Armstrong. I'm a junior in aerospace engineering, and I'm focusing on aerodynamics.
I'm Anthony Demuria. I'm a senior in aerospace engineering, and I am the manufacturing sub-team lead.
My name is Benjamin Heckel. I'm a sophomore in aerospace engineering, and I'm a member of the engineering sub-team, or the manufacturing sub-team, excuse me.
Oh. Wonderful. So we're going to start sharing our screen here.
Yeah.
But like I said, we're Project Zephyr. We're the Supersonic Recovery Systems we're the Supersonic Recovery Systems Research and Development Project here at Embry-Riddle in Daytona Beach, Florida. We just introduced a large part of our team, but we are over 30 undergraduates working on this project for really the last couple of years, and we're on our second iteration of our launch vehicle. So yeah, we have three main objectives as making safer supersonic systems, which is an alliteration in itself. But our first goal is to make sure that we're safe. Not only that we're safe, but we're making safe products. So we are developing a recovery system that is going to be safer for use in the industry and for use for us. And then our second thing that we're working on is making it more reliable, and that contributes to the safe aspect. Making sure that the recovery systems open consistently almost every time, a certain percentage of the time. And that is the second thing we're focusing on for our recovery systems. And the third thing is to make sure that it's cost effective, which also means time effective, making sure that the maintenance doesn't take too long, making sure that it's pretty cheap, it can pack into a small space, basically take as much not a lot of cost or volume in any system that we are going to be putting these in. So we had our first rocket, which was Zephyr 1. This is the nominal concept of operations here. We launch the rocket, the booster flies away as soon as it's done burning, and that it gets recovered on its own. And then the top, within a second, the experimental parachute comes out the back and is experiencing supersonic forces. And then it coasts gradually down until about like 1,000 feet, where the main parachutes deploy or joke, and then main parachutes deploy off the dart, and then we go and recover it. But unfortunately, when we launched it, that's not how it went at first. As you know, things can go wrong sometimes in rockets, no matter how much we prepare. So we did launch our rocket, and we got the booster back, and we got the parachute, experimental parachute back, but unfortunately, we lost the dart in the jungle of Florida. So we were able to recover the parachute. If you want to go to the next slide. We have a couple of launches, views of the launches here that we want to show with you guys. So yeah. That's what we had, and here's the one with the sound. Sorry if it's a little loud.
Oh my God.
So we were all super excited that this rocket launched. We worked very hard on it. And so we did launch this single stage boosted dart configuration on an M3700 motor. Its top speed was about Mach 1.4 that it actually reached, and then the parachute deployed at Mach 1.38. So it slowed down fairly quickly. We did not get the dart back, like I said, but the parachute detached throughout flight. So it did experience the forces. We just didn't get the dart stage back, which is what we're trying to improve upon on this next rocket. And so we have Zephyr 2. Zephyr 1 was our first iteration. Zephyr 2 is our new launch vehicle that is more improved, more modular, more cost-effective for our testing reasons. So here's a rocket overview. There are 3 different parts to this rocket, 3 separate sections. We have, going from the bottom to top, we have our first stage booster, which houses our largest motor and avionics and its own recovery system. Then the second stage booster, which has our secondary motor and avionics system and recovery system for itself. And then our dart stage, which has our data acquisition, additional flight computers that we need, and avionics bays, as well as the experimental parachute and the main and drogue chutes. So we'll kind of go through that. The dart stage, next. I kind of labeled it here a little bit. We're going to have 2 separate avionics bays in the dart stage. So as you can see, there's going to be one in the nose cone. That was recently added because we're going to try live streaming video footage and data back to us by the launch field. And then we're going to have our drogue and main chutes. And we're going to have the dart avionics bay, which has our load cell in it that we're going to make sure that we're measuring the load from the experimental parachute. Our connection point, which our structural team will go more into detail on, basically anything to help with stage separation, so our black powder charges, and those are those red arrows right there, our separation points, and then we have the experimental chute in the back that has 2 cameras attached to it as well. Our second stage booster has its main chute and then the avionics bay that includes separation and ignition of the second stage motor. And then we have what's called an exterior coupler for us. Since we are a minimum diameter rocket, it is a little bit to stage our engines. It's a little bit difficult. So instead of having the extra drag, frontal area drag, we are having the skinny rocket and then just having one external coupler to kind of hold the top stage onto the second stage while it's being boosted. And manufacturing can go more into that in a little bit. And then our last stage is the first stage. There's just the main chute and the avionics bay, again, for separation and deployment of the parachute. And here's some of the general info. I won't go over a whole ton of it. If you want later, we can go back over it. Apogee for our configuration that we're going to be launching, which our first configuration is going to be 2 L2200s, is about 12,000 feet. We like padding the number a little bit just to make sure we're not going over waiver. And our max speed is going to be Mach 1.5, 1.6, around there. And we're going to have a lot of acceleration, about 20.2 Gs of acceleration. But if you notice, this is a really long, skinny rocket. We like to joke that it's called a pencil. It is a little over 14.5 feet long and 3 inches in diameter, so very high aspect ratio. And its mass with the motors is just over 51 pounds. So it's a pretty heavy rocket, but it also is pretty skinny, making sure that we can go straight to supersonic as fast as possible. We have a lot of different motor configurations. These are only 3, but we can also launch the rocket with just the second stage booster and the dart stage. And the stability, which my stability and MATLAB team will talk about a little more. We have it a little above 3 right now, 3 calibers of stability. And we have 5 different parachutes on this rocket. So there's a lot of parachutes, a lot of ejection charges, and a lot of separation charges that avionics is in control of. But that's the CAD or cross-section of our CAD of our rocket as of right now. So here's the concept of operations. You can just click through it a little bit. We have our launch in the beginning, and then we have our first stage separation from our first booster to our second booster, and then that first booster is going to recover, so parachute deployment. And then we have a second stage separation, which is about at 4 seconds, 5 seconds into the flight, so pretty quickly. We're getting supersonic pretty quickly. and that's the stage separation between the second booster and the dart stage. And then the second stage, the first stage, the dart is going to deploy the experimental parachute, not even a full second after stage separation, just to make sure that the booster gets out of the way before we eject the parachute at the bottom. And then the second stage is going to deploy its parachutes and come down nicely. And then after apogee, if the parachute does not work, experimental does not work in any shape or form, then at an apogee of about 12,000 feet, then the parachute will deploy for a drogue chute for the dart stage. So the full flight time with landing is about 11 minutes, but the whole mission is completed in about 6 seconds. So that's a pretty quick time frame that we have to deal with, especially with avionics wise. And so here are the recovery systems. I know it's me talking a lot. I apologize. They'll get to talking soon. So we went through a huge brainstorming process for our recovery systems. Our first launch, we used a disc gap band parachute, but now we are trying to do our own. So we have a couple of our designs here, a couple of our brainstorm sessions that we thought up, and then here are some that we're preparing actually for test, drop testing. We're gonna go into a large stairwell in our college, and we're gonna start dropping them, measuring the descent rates, which one works the best subsonically, and then we'll use that data to interpret what we're going to use for our supersonic test flight, and then we can add on to those as we get further.
So just a quick summary of the aerodynamic team's goals have been to obtain the trajectory versus time of our rocket, as well as the stability. We also want to make sure that our rocket doesn't exceed the altitude limit at our launch site. It's also very important. Previously, we would use OpenRocket for our whole simulation, but OpenRocket's accuracy begins to suffer in the transonic and supersonic regions. So we are trying to develop our own codes for our own purposes to obtain these quantities. So we're developing Berriman's supersonic stability equations from his paper into a usable code, and we're also developing a trajectory estimation code. So just a quick overview of the trajectory estimation code. So it's based off of the rocket equation. It's a statement of Newton's second law, right? It sums the forces on the rocket. However, that equation cannot be solved analytically. You can't just get a closed form solution, or you can just plot the velocity, acceleration, and position versus time on a graph with a nice smooth curve. So what you have to use instead is a numerical method. The picture on the right is a pretty good summary, a good visual illustration of how the process works. The code determines the velocity contributions from each force. So obviously thrust is a positive contribution, gravity is a negative, and drag is also a negative. In this case, we're assuming zero angle of attack, so there's no lift. But through each iteration, it builds off the last, and eventually what you get is a smooth curve of velocity. And you can integrate velocity to get your altitude, and you can take the derivative to get your acceleration. And in the end, we get a very good approximation of velocity, position, and acceleration versus time. There are some drawbacks. We're relying on previously existing data. We're using engine thrust and engine mass flow rate data from the manufacturer, which is tabulated, so it's not exact, it's just an approximation. We're also using the ISA atmosphere model, which is accurate within our flight envelope. Additionally, we have to determine drag on our rocket. And this is a difficult value because typically this would be determined empirically, or sorry, not empirically, but determined experimentally with wind tunnel tests. But we don't have the funds for that, so we are looking into other methods, such as empirical methods from many years of missile tests and missile experimental tests in wind tunnels. And we're also looking into doing some CFD simulations to determine the drag.
So as Eric stated, we need the drag coefficient values for our trajectory code. So that's what this whole section is about. We need it for the trajectory. And also we're trying to get these coefficient of drag values to match up between different models that we use. So when we start going into CFD, if we get coefficient of drag coefficient of drag values outputted from CFD, we want to check it with something else. So the more we check, the more we can trust that value. So the model that we use is based off of AIAA's education series, Missile Design and System Engineering by Fleeman. And in that model, there were a few assumptions. The first of which is that there is no boat tail, and the boat tail is placed at the end of the rocket, which reduces the pressure drag, and it basically controls the wake, minimizes the wake effects on the drag. And in this model, it's called the base drag. Another assumption is that there was a gradual change in the speed of sound and viscosity, and in the altitude that we're going to be dealing with. That's true. And then also it assumes that there's a turbulent boundary layer, and because we're going at Mach speeds, we will definitely be having a turbulent boundary layer. So the coefficient of drag model does have some limitations. The first of which is that it assumes a linear aerodynamic model. What this means is it essentially adds up the coefficient of drag for the various rocket components. So for example, it computes the coefficient of drag for the body, and then it computes the coefficient of drag for the sets of fins, and it simply adds up those values to get the total drag. So what this means is that it won't account for the fin interferences between the different sets of fins. And for our rocket, we have multiple sets of fins, so that might be something to keep in mind as we move along in our analysis. Also, there's no information directly related to the transonic flight regime, and that there's also no output for Mach equals to 1, which when you look at this figure to the right, you see a discontinuity, which is expected for this model. Next slide. So we ran a model with just the dart stage. So we inputted the geometry specs for the fins and the body of the dart, and this is the output once we got the model into MATLAB. As you can see, there is a discontinuity at Mach equals to 1, which, as by the previous slide, this is expected, and it outputs values for both subsonic and supersonic. And this is a general shape that we would expect when you look at some other textbooks about variance and coefficient of drag. This holds to and it matches that shape. So we've come up with this iterative evaluation model, and this is to make sure that we can get the most accurate analysis code that we can. So we start with the drag coefficient values, which we now have, and we've incorporated them into a script. And now we're going to use those values and insert them into our trajectory code, which Eric talked about. And from there, then we're going to start matching it with flight data. So we're going to take a known rocket case where we know the geometry, and we also know the trajectory from the flight data, and we're going to match that with the output of our code. If it doesn't work, then we'll go back and look at the specifics of our code, make sure the assumptions are correct, or maybe add some more details if some of the assumptions cannot be made. And then we'll keep checking and keep checking until it works. When it does match, we'll then start applying it to our Zephyr 2 rocket. And then from that point, we'll be able to check the requirements such as altitude to make sure that we meet those requirements.
Yeah, so what you see here is the first CFD simulation that we performed that we actually used to influence the design of the rocket. So right here is a static pressure contour plot of a simulation of one of the fins from the dart stage. This is the chamfered configuration, and this was run at Mach 1.4. The purpose of this simulation was to compare the drag result from a chamfered fin versus an unchamfered fin, because chamfering fins, especially composite fins, can be quite difficult to get a consistent angle. So we wanted to make sure that if we were going to put in the effort to do that, we'd get a significant result. So as you can see here, this fin produced a drag, total drag, including pressure and skin friction, of 115 newtons. Next slide. Immediately, you should be able to see the change in the flow structure because we're using the same contour colors. You can see the bow shock at the front moved away from the fin, and it's also at a steeper angle. It indicates the flow is having to slow down faster, and there's a higher pressure at the front. And as you can see on the right side, the drag is about 50% more, which is quite significant. So I bet you can expect which fin configuration we used. Those simulations are not validated yet. We don't exactly know how to do that, but we're learning. That's one of the main goals of the CFD team, is to learn how to use CFD correctly as an aerodynamic analysis tool. We want to make sure that we validate our simulation methods. We want to make sure we're able to verify our results. And we also, in the future, want to be able to determine the error, so we can figure out possibly when we plot our trajectory what the upper and lower bounds of our maximum height, velocity, and acceleration might be. Once we figured out how to verify and validate our solutions, some of the goals which we would like to accomplish are validating the empirical model, which Spencer talked about, validating the center of pressure data, which Graham will talk about for the stability calculations, and to fill in the data in the transonic region where the empirical model doesn't provide any results. Currently, the software that we're using for our preprocessor, you can think of that as it's kind of like CAD, but for CFD. You build a computational domain, which allows you to simulate the flow around the body. The software that we're using for that is ANSA by Beta CAE Systems, our sponsor, and Fluent's preprocessor, as well as Pointwise. We have a bunch of different people on the team with a bunch of different skill sets. Some people prefer some softwares over others. For our solver, we're using SU2. It's an open source CFD solver, and we're also using ANSYS Fluent. For our post processor, we'll be using Meta, again, by Beta CAE Systems. And lastly, we're still trying to figure out how we're going to run these simulations. The 2 fin simulations I showed you were run on my laptop. It got very hot. There weren't that many cells. It was only about 40,000 to 80,000 cells, which is not a lot. There was a simulation that I ran over the summer on a supercomputer that had about 4 million cells, and that took about an hour still. So our goal here is to find a way to run our simulations on good hardware for not that much money. So we're looking into AWS or Microsoft's cloud services. They essentially allow you to rent out time on a supercomputer, so you don't have to pay to, install the supercomputer and pay for the electricity bill of running it for hours on end. So yeah.
So this is the vision, the future vision for the aerodynamics team. We want to make sure that we have all the aerodynamic parameters, such as the drag coefficient and normal coefficient. And we also want to establish a credible trajectory code, which was referenced, and how we were going to do that was referenced in a slide a few slides back, which was that iterative evaluation. We keep checking it and rechecking it, and then that loop. And we'll keep revisiting these points as we to do flight tests and get flight data and check out the flight data. And for the farther along goals, we want to optimize the Zephyr 2 geometry where we can, maybe like nose cone, changing the nose cone geometry, or adding boat tails, or doing some adjustments to the fins. And also we want to look into two-way FSI for parachute behavior, that being the fluid structure interaction. And this will give us more accurate CFD results, because instead of a static mesh, we'll start taking into consideration the dynamic effects that mesh has.
So, supersonic stability. This has been a year-long attempt at recreating James Berriman's supersonic code from his thesis paper back in the 60s. We have successfully been able to validate the results with what he got in his paper for a tomahawk fin. The only caveat now being that for calculating things for the entire rocket, it uses subsonic calculations for the nose interference factors, simply for the sake of ease. And we will be adding those in later on, hopefully sometime this week. And as you can see on the bottom there, I have up the stability for the full rocket as a function of Mach number, and as a function of Mach number and angle of attack. And as you can see, we very, very briefly are going to become unstable, but in terms of the actual rocket's flight, that will be a very brief period, if there at all. And here are just some more graphs showing what it would be like for different stages of the rockets together. We have the full rocket, which was on the previous slide, and then with the sustainer stage and just the second booster, and then the sustainer only. And as you can see, that little dip is the only time that our rocket will ever be unstable. And for the future of supersonic stability, we will be looking at developing a stability versus time graph for our trajectory based off of the trajectory code that we are making. We will also be applying it to our code for aeroelastic divergence, which I'll go over in the next slide. And we're going to incorporate those supersonic nose cone and interference factor calculations. So for aeroelastic divergence, he's not here with us right now, but one of our members has developed code to determine our fin flutter. He did it based off of a model given by an Apogee newsletter, and confirmed them with AeroFin Sim 10. On the bottom there, you can see the table of values for our flutter speeds, both hand calculated and calculated through AeroFinSim. And as you can see, the calculations by hand were pretty accurate for the boosters, but for the dart stage, not so much. So we'll be going with our AeroFinSim results, as we'll find them to be more accurate. And you'll also notice that the speeds at which we'll experience fin flutter are going to be higher than what we would normally experience during flight, which would be very good because we're not going to be having fins breaking off during flight. And then we will also be developing a version of Chris Flanagan's FlexRock, which will use supersonic calculations and will help us determine whether or not the rocket will snap in half during flight, which would be, to put it lightly, very bad.
Okay, so now we're going to talk about structures. So as you've seen, we're going to be ejecting a parachute at a very high speed. And so one of the main goals of the structures team is to make sure that the rocket doesn't fall apart when that happens. And so we actually calculated that we would be seeing up to a 5,000-pound peak load on the rocket when the parachute deploys, which is a lot. And so just to give a little bit of context, that image you see in the upper right, as you've seen, that's kind of the area where the experimental parachute is attached to. So that red box there to the back of the dart stage. And below that is a cross-section from our CAD of basically the system that will be retaining the parachute when it deploys. So we kind of took what seems to be a little bit of an unconventional approach when making this. You may notice there's no U-bolts or I-bolts or even a threaded rod through the avionics bay, and I'll explain kind of why we took that approach. But the way it works is that the shock cord is actually looped through those two big holes in the bulkhead, so it's tied directly to the bulkhead. And the bulkhead is disconnected from the avionics bay itself. That's why there's no threaded rod. And the real reason we decided to do this was because just in case something did go wrong, we wanted to make sure that the avionics bay would still be okay, right? It contains all of our flight data, our footage. So if something did go wrong, the two systems are sort of disconnected. So that kind of fits with our theme of safe and reliable systems, right? Of course, though, we don't want things to fail. So a big part of what the structures team has been working on has been doing analysis. So first, we did hand calculations. So basically, these involved determining the number of set screws we needed to hold the tube together, as well as epoxy shear strength. So to kind of explain it a little bit, the bulkhead that you see in the middle there, that experimental bulkhead, it's sort of sandwiched between two different coupler tubes. The dark gray ring that you see is the load ring. It's basically a piece of coupler tube that's epoxied to the inside of a body tube. And that's basically going to be pressed, the bulkhead's going to be pressed against that when the parachute deploys, and that's what will be transmitting the load to the rest of the rocket. So that's a critical component, and it will also need to be tested. We did more analysis on things like the shock cord tensile strength to make sure that wouldn't snap, which would be very bad because then we lose the parachute, as well as doing analysis on the aluminum bulkhead itself, which we'll talk a little bit about on the next slide. So that's a picture of the bulkhead. It kind of looks like a very thick slice of Swiss cheese, but there's a good reason why there are so many holes in there. It's a very complex structure because there's a lot of functionality associated with this. There's going to be charge wells on it to eject the parachute. There's going to be a hole for a camera. There's going to be the two big holes you see there. That's where the shock cord is going to be looped through. And so to simulate this, we assumed a 5,000-pound static load. So that's not entirely true, right? I mean, in reality, it's only a transient peak load, but we figured that if we tested it and designed it to withstand a 5,000-pound peak static load, that it would be okay. It's a conservative estimate. And so that red area you see in the top left image, that's where we decided to apply the load in our simulation. It sort of simulates where the shock cord will be pressing against the bulkhead. As I explained before, it's going to be kind of looped through as opposed to tied to an I-bolt or a U-bolt. And below those two images, you can see the actual results. So we designed it for a 1.4 factor safety for yielding. And all of this was done in ANSYS Mechanical. And the actual design optimization was done using ANSYS Workbench. So the thing we have control over, really, not the holes, those kind of have to be there, is the thickness. And so we used the parameter optimization in ANSYS Workbench to determine the minimum required thickness for the bulkhead, which I think was around 12 millimeters. So that's why it's so thick, so that it can withstand the load. Of course, analysis is great, but it's also good to have, validate that analysis with testing. And so we plan on doing a full structural test, sort of this compactified model. So you can see in that bottom image is basically what's in that top image, except it's shortened. All the same key parameters are kept, like the size of the load ring and bulkhead, number of set screws. It's shorter though, because it's going to be clamped on both ends. And it's actually going to be tested up to 5,000 pounds in the Embry-Riddle Structures and Instrumentation Lab. So we plan on doing an actual test, and this will really help us validate our design and our analysis, and we hope to learn a lot from it.
So for manufacturing, our sub-team is responsible for we're responsible for the physical construction of the structural components of the rocket and the stability components of the rocket. We get to work with hand tools and power tools in the composites laboratory because of a lot of our materials that we use are composites. I actually have some physical visual aids that I hope you guys can see. This is one of our body tubes that we talked about earlier. It's 3 inches in diameter. It's made of fiberglass. We order the fiberglass and it comes in longer tubes, and then we cut them down to size and sand them. This is part of our stage 2 booster. It's one of 2 body tubes in that stage. Here, made of the same material, I have a cut and sanded coupler tube, which is a smaller diameter that actually fits inside the body tubes. It also has on it a switch band, which is the same diameter as the body tubes, that's epoxied in place. So when I slide it in like this, it stays like that and allows us to put another body tube on top, and it contains an avionics bay inside of this coupler tube eventually. Not right now, obviously. As Rebecca mentioned earlier, we have one coupler tube on the rocket that is a larger diameter than our body tubes. This was actually not ordered, it was made in-house with the cooperation of another part of our club, EarthSays, our project Acme. It's made of carbon fiber and it's completely untouched. That's why it's bunched up at the ends. This is just the raw product. It's only been produced. We haven't cut or sanded or anything at all. Right here, I have one of our fins for the rocket. It's made of a carbon fiber laminate plate. This is for the first stage booster, which is the largest set of fins we have. All 3 boosters have different fins with, a lighter background so you guys can see it. They all have different size fins with different sweep angles, different trailing edge angles. And currently what manufacturing is working on is a solution to making a chamfered fin. So chamfered leading edges and chamfered trailing edges for better airflow over the fins at all stages of the rocket. And this, I just grabbed this before the presentation because I almost forgot it. This is a fin jig. So what we use this for is how we mount the fins to the rocket. We put the body tube in it like this, and this fin doesn't match this fin jig, so I apologize for that. It's going to be a little wonky. Let's see if I can get this in frame. But it basically slides in like this. So it stays in place while we are epoxying the fin. Is that good? Yeah. While we're epoxying the fin to the body tube, and then once that's dry, we remove the once that's dried, we remove the fin jig, and then we lay for this rocket we are going to put 3 layers of fiberglass on top of the fin in order to make sure that there's no to make sure that they don't fall off the rocket, make sure they're secure in place. So
okay, so as Rebecca mentioned in the beginning, we have 4 avionics bays in Zephyr. One is in our booster, our first booster, one is in our second booster, and then we have 2 in our dart stage. All of our avionics are controlling our stage separations, our parachute deployments, motor ignition, and also our data acquisition. So for the dart, we have 2 avionics bays. One is just for data acquisition, and then we have our main bay that is actually controlling everything. In our main bay, we have 2 flight computers, a Blue Raven and a Telemega, and those will be collecting data and controlling all of our parachute deployments and separation charges. For data acquisition in this avionics bay, we have a Raspberry Pi, and then a Raspberry Pi camera as well, and that is going to be watching our experimental parachute, so we'll be able to view it later. We also have a load cell in this avionics bay, so we can collect data from our parachute being deployed. And we're going to be using LoRa modules to send that data back down to us so we can watch it live during the launch. And then we have a second avionics bay in the dart stage, our data acquisition bay, which will have another camera pointing down from our nose cone. And we are looking into using that to stream so we can get a good view of our rocket from the ground. For our second stage, it's going to be controlling our motor ignition. And we have 2 flight computers in it, a Telemega and an AIM Extra. We're using these 2 because they have gyro modules on them. So that way our rocket won't ignite if something goes wrong and our rocket's horizontal. And then our first stage avionics, we also have 2 flight computers, a Blue Raven and a Telemega. And like our dart stage, those are just collecting data and then performing our separation charges and parachute deployments.
So overall, we have done a lot of work, our whole team. However, we have a lot more work to do and some things that we want to do in the future. So 3 particular things we want to do in the future is, first, once we have a successful flight, either this month, this next upcoming month or March, we want to make a more dynamic, flexible to rigid system for our recovery system. So basically start off with a parachute that's packed extremely small, resembles more like fabric type of thing, and then it can expand into a stiff structure once it's being deployed, basically forcing the parachute into an open configuration, making the deployment more reliable for the recovery system. And then the second thing we are looking into currently is with our other EarthSEDS project, ACME, our manufacturing sister project. We are working on seeing what kinds of cheaper materials we can use and how we can manufacture our rockets more efficiently. And the third thing kind of falls under materials as well, but also the design of the rocket and the packing techniques used for it, the parachute, is how easy it is to use and maintain. So really developing the packing techniques. I did a presentation last NARAM, last R&D NARAM on different packing techniques we used for the first Zephyr rocket, but now we're trying to make those a little better, make sure that there's not a lot of friction going on and melting our parachute. And then adding more of the low maintenance. It doesn't need as much time to check over before each launch, so we can launch a lot more and test a lot more, basically so we can have more materials and cheaper and lighter materials so we can get to different higher speeds as well. But before I ended this presentation, I wanted to thank our sponsors. We have 3 specific sponsors: Beta CAE Systems and Onshape, and then of course our university, Embry-Riddle Aeronautical University in Daytona Beach, Florida. Without them, none of this would be possible at all. We're definitely doing a lot of good work, and with their support, we're going to continue doing our best work and learning to do more. But if you guys wanted to be a sponsor of Zephyr, we have a couple of different ways that you can reach out to us on the next slide. Whether you want to add us on Instagram or email us, those are our 2 top ones there. And then we also have our website if you want to check out any of the other stuff that EarthSEDS is doing as a whole. We also keep that page up to date for Zephyr as well. But now I see there's a couple different questions coming in the questions tab. We'll go from the oldest. So first, thank you guys for listening to our presentation. We've all put our heart and souls every weekend and day of the week into this project. And we're going to do our best to answer your guys' questions. But we are students, so we're still learning some of these things. But the first question is from Stanley Max. about what kind of simulation program are we using for the concept of operations graph. So for our initial kind of approximations, we're using OpenRocket, which is an open source trajectory calculator that gives us all of our main assumptions that we're going to use, and then we're making our own software to basically either validate those or make them more applicative to Supersonics. So I hope that answers your question. That's what we used for that one. It's basically to lay out our design initially and get some initial approximations, since we're not too far over Supersonics yet. And then the next one is from Bob Zurich. Hi, Dad. I'll give this one to Graham to answer, but when you are mentioning going unstable, is the rocket just going below 1 caliber stability and remaining positive, or actually going negative?
Yes, so I did perhaps misspeak there. We are just going below 1 caliber. We are not at any point going to be going negative.
Cool, so it's going to be a safe flight, and we're going to be transonic for not even full seconds at a time. Like I said, our whole entire mission is completed in 6 seconds. That includes both the first and second stage burning and separating, and the parachute coming out. And that's actually a little over how long our mission is going to be. It's really 5.5. So then the next one, let's see, David Carter. What are you using for your shock cord that can withstand that force? So we are using some tubular nylon. Sorry. We are using tubular nylon, and we are wrapping it multiple times to create what's called a riser, basically the connection point between that structural system and the shroud lines of our parachute. And from our shock cord and shroud lines, our shroud lines are going to be made out of Kevlar cording, braided Kevlar cording, to also help with that. But we're going to have a couple of systems that we didn't go into too much detail here. We're going to have that looped tubular nylon, and then we'll have an external cord that, in case for some odd reason that tubular nylon that we did calculations with doesn't withstand that force, there's an extra way that we're going to sew some of the shock cord to make sure that it doesn't break immediately and can handle some of that extra force by breaking threads that we sew in there instead. So our load ring, what epoxy will we use for the load ring by Gary Leach? We are using, Patrick?
I think it's the West. Right now, we're planning on using the West.
Yeah, we're using West Systems
The
502.
I think it's we're still planning on using the 5-minute epoxy right now from Gorilla Glue, but we're not sure yet. We're still doing analysis. We were able to show that the 5-minute epoxy was sufficient to withstand the load, which will be verified when we actually do test it.
But we're not sure if we want to make a redundant, like super strong.
Yeah,
epoxy.
we're still doing some calculations and analysis whether to do 5-minute for how quickly it cures, or a resin epoxy that we're using for, like, example, laying up our fins for our fiberglass. But we're using either West Systems or Gorilla Glue 5-minute for that. Okay. From Casey Willett, are your documented videos of the project, specifically the launches and the upcoming launches, posted on YouTube? Good question. So we're definitely getting more into the PR aspect for EarthSEDS as a whole. EarthSEDS does have a YouTube channel that we are going to be posting more full videos on. These first Zephyr videos are not posted on there, but where they are posted, if you guys have Instagram, we keep by like a monthly post on our Instagram page for Project Zephyr, where we post videos, what we're working on, little things, little snippets of what we're doing. Sometimes we post some new CFD things, stuff like that. Ken Birkin, I'd like to know more about the high-speed parachute itself, not just the rocket, please. Okay, so our parachute, we are currently going through more analysis of what particular parachute we are using. We have a couple of different designs based off of designs previously done by either other companies or the military. We started off with a basis of a disc gap band parachute last time. So basically that's a disc canopy with a little bit of a cylindrical ring underneath it, and that is typically used for supersonic recovery. Another type is a conical ribbon parachute. We have definitely looked into that, but that does take up a lot of weight for us and is very difficult for our team to sew and learn about. So we are trying to, design different unique options. We don't have them currently with us right now. We're going to be drop testing them soon. But we are going to keep up to date again on our Instagram and probably our website of the parachute that we decide to test. We have gone through different shapes, different materials, different configurations. We're trying to do some things with mesh, which is why static CFD is not as viable of an option for us currently. And we'll keep you guys updated on that, and hopefully next year for VNARCon as well, depending on how well you guys liked us. And then finally from Bob Kaplow, any info about designing a parachute for that speed? Like I said, we'll keep you guys up to date more on the actual parachute itself. Right now, we are going to have our first test flight for one engine, just to make sure that all of our systems work. And we'll have basically a dummy parachute for that first time. But we are doing drop tests. Actually, today's Saturday. We're doing drop tests tomorrow to pick which parachute we're going to use. And then we're taking videos of that drop. Each drop we're going to do a couple different times. And so we're going to go frame by frame through all of those videos and see what the descent rate is and calculate that out. See which one works best subsonically, and then see how well that's going to work supersonically through our tests. We had a couple of the designs before. We really had almost like a blue sky brainstorming session. So we went through and, had a bunch of different designs that we drew out. And I had a couple of those pictures before, whether it was, if you want to go back to that slide a little bit, it's like slide 10. And so we wrote down on basically a piece of notebook paper for each of us, and we wrote down all these different types of parachutes, whether it was 2 parachutes in one, or whether it was a full mesh parachute like we're showing here, or a cross parachute with some mesh in it, kind of to help that with that spacing technique. Those are some of the parachute designs that we were thinking of, or looking into more unconventional parachutes for rockets like Graham Air parachutes as well, which is like that bright white parachute in the upper right-hand corner there as well. Harlem Lily, how many people are on the Zephyr team right now? So we have a lot of different members. Currently, we have over 30 undergraduate students, undergraduate members. I would say our last meeting had 25 and not everyone was there. So at least 27 active Zephyr members. I've counted over 30 at many different meetings, and it is consistently rising. We recently had 4 or 5 new members join for freshmen this past meeting. And we'll see what happens if they come back or not. But we started with 6 people originally a couple of years ago. And then we just grew that, and we're now a big, happy Zephyr family, doing CFD work and MATLAB and coding and supersonics in general. So we have a really big team, but everyone's doing something, whether it's PR, technology, manufacturing, actual calculations. Everyone's involved in that. Okay, another one from Bob Zurich. On the initial rocket launch, did the first experimental parachute survive the deployment at supersonic speed? And if so, what was the failure mode that caused the dart to be lost? So, does anyone else want to weigh in on this, or should I just tell the story of Zephyr 1's parachute?
Go for it.
So, The experimental parachute did survive the launch. We have it. We have the actual experimental parachute. It can fly again. Has some minor Kevlar burns from the friction of it coming out of the tube. And we actually have a picture of it floating away with something on the bottom of it that we didn't show in this presentation. But we are not exactly sure what exactly was the failure mode to cause the dart to be lost, which is why we're trying to over-engineer this current design, beefing up the structures that are holding the parachute, as well as the physical shot cord line itself. All we can tell is that at some point within the 2 weeks that we launched to when we found the parachute, the shot cord broke off of the recovery system, retention system. But we have no idea if the actual retention system, like the threaded rods or the eye hooks broke, or the glue separated, anything like that, which is why we're trying to over-engineer this rocket as of right now. But I think that answers all the questions. If anyone has any other questions, just type them in the chat and we will get to them. If not, thank you guys so much for viewing our presentation. We love presenting to you guys and hope to do it again in the future with an update. I'm looking in the comments, I don't see anything. And thank you guys for all of your support too. But enjoy the rest of VNARCon. I don't see any more questions coming in. And I guess it's the end of our presentation. I'll stop sharing if you want.
Bye.
Oh, not stop broadcast.